Hello. Today we introduce Giraffe 2.0, a new technique using radar for 3D reconstruction of objects inside a box. Vision methods today produce impressive results from multi-view images, view synthesis, surface reconstruction, and relighting. But what if the object is hidden inside a box? Thanks to the cheap and safe penetration of radio frequency signals, we use millimeter wave radar to see through it, enabling non-line-of-sight 3D reconstruction. Giraffe reconstructs both the box and the object hidden inside it, with accurate surface and shape. Let's start with radar imaging. Unlike a camera's pinhole aperture, which forms a clean image, radar has no aperture, a regime known as lensless imaging, so its raw signal is pure noise. Radar measures the time delay between transmission and echo. With an FMCW waveform, mixing the transmit signal with its delayed echo yields a constant frequency tone whose frequency depends on distance. For each voxel, we compute its distance to the antenna and multiply the signal by the conjugate phase, isolating its contribution. Across many antennas, these contributions aggregate into points, forming the image. Similar to vision, we sample points along rays. An MLP predicts 3D geometry. From this, we simulate the RF signal and compare with the radar image. To simulate the RF signal, we model two parts, the wave and the amplitude. The wave follows directly from the signal's propagation distance. The real challenge is simulating the amplitude, which depends on the surface geometry and the radar's reflection behavior. Let's first see how vision handles rendering. The object's surface can be represented by a signed distance function, the distance from any point to the nearest surface, positive outside, negative inside, 0 on the surface. Moreover, the gradient of the SDF yields the surface normal at every point, a key quantity for radar reflectance modeling. In volume rendering, the weight along each ray is the product of accumulated transmittance and opacity. Following NLoS, both can be derived from the signed distance function. Opacity is obtained from a sigmoid of the SDF and transmittance accumulates from the opacities along the ray. Returning to the radar domain, we adopt a Lambertian factor to model radar reflectance. The signal amplitude at each sample is decomposed into surface reflectivity, the Lambertian factor, free space power decay, the squared transmittance accounting for the round trip, opacity, and the emitted signal amplitude. However, tracing signals for every antenna in the array is computationally prohibitive. Unlike vision, which traces one ray per pixel, radar must sample many rays per antenna, incurring a higher-order time complexity that makes real-time inference infeasible. However, since the 3D scene is common across all antennas, we share a single set of parallel ray samples across the entire array. Note that transmittance cannot be naively reused across antennas, since it depends on the accumulated opacities along each individual ray. Recall, however, that in NLoS, transmittance is expressed as the sigmoid of the signed distance function. We therefore correct the shared transmittance using the sigmoid of the SDF at the per-antenna boundary. Scene representation also differs. An object inside a box cannot be simply divided into inside and outside. With line-of-sight and non-line-of-sight regions mixed, we define positive values as free space and negative values as the box shell and the enclosed object. The SDF is the distance to the nearest surface. We call this the Unified line-of-sight SDF. Recall the lensless rendering scheme. To handle each antenna independently, we correct the shared transmittance by multiplying it with the sigmoid of the SDF evaluated at the antenna's boundary point. Fortunately, the line-of-sight region is identical in both scenarios, so we reuse a vision pre-trained SDF to compute the transmittance correction. The next challenge is surface ambiguity. Unlike RGB images normalized to 0 to 1, the radar signal is unnormalized. As a result, SDF values can be globally shifted, making the true surface level ambiguous. We call this a relative SDF. The key insight is that, in the line-of-sight region, the SDF should be exactly identical whether trained from vision or from radar. We therefore render the line-of-sight distance along each ray and minimize the discrepancy between the vision and radar predictions, anchoring the entire surface to the correct level. Let's see reconstruction results by Giraffe 2.0. It successfully reconstructs both the outer box and the enclosed object, recovering accurate geometry as well as the correct surface level for each. Thank you for your attention.